In this example, we're going to solve a polynomial inequality, more precisely a cubic polynomial inequality. Let's read the problem. First, plot the function 2x cubed minus 5x squared plus x plus 2, and then solve the inequality obtained by taking the same function 2x cubed minus 5x squared plus x plus 2 and setting it greater than 0. So that is my inequality. Okay, so what was the plan for solving polynomial inequalities? The plan was first ensure that the right hand side has 0. That's already the case here. And the first difficult step was to factor the polynomial. How do we factor a polynomial? Well, we set it equal to 0 and find the roots. And now, we have not studied a formula for solving a cubic equation with you, but there exists such a formula. It's called Cardano's formula. But that formula is it is very, very large, so it wouldn't fit on this slide if you do the full formula. So it is not practical to use such a formula on an exam. This problem. In this problem, I'm going to assume that we have access to a graphic scientific calculator. So once again, when solving this problem, I'm assuming the presence of a graphing calculator. So that problem would not be suitable for an exam where you don't have such a device. Okay, so let's plot the function. Since I have my graphing calculator, I can immediately plot the function, and here it is. Here's the graph of my function. Here are the scale indicated by my graphing calculator. This is -1, this is 1, this is 2. Okay, so now using this graph, can I quickly factor my cubic? Oh, my cubic must factor, well, if it were to be factored, it would have to have 3 factors because it's of degree 3. And it may have also a coefficient here. So, can you quickly guess the factorization of the cubic using the graph? Can you do that? First, can you guess what to put under these 3 question marks? And after you're done guessing that, tell me I'm going to ask you what to put under that question mark. So, can you first guess what to put here, here, and here so as to make this factored? I'm sure you guessed it correctly. What you need to put in these positions are the roots of the polynomial. So these are the places where the graph of the function intersects the x-axis. So what I'm putting, the numbers that I'm putting here are the places where the graph of the function meets the x-axis, the x-coordinate of those points. Now, you're going to say, okay, it was fairly evident that this tick mark, the tick mark at 2, exactly met the graph of the function, and it was clear that this tick mark here exactly met the graph of the function. Well, maybe if I were to zoom in with my graphing calculator, they wouldn't fit, but at least it's believable that these 2 numbers are 1 and 2. That's believable. But this number, -1/2, how did I spot it? It looks like this point here is exactly the midpoint between -1 and 0, but am I really sure? And what if my eyes are deceiving me? By the way, even with a real graphic calculator, in a real exam, you may experience the same problem, right? I mean, you'd have to zoom in with your graphing device to be sure that your approximations are correct. And even then, you can't be perfectly sure. But let's first assume for a moment that we guessed it correctly. So let's assume that, okay, 1 and 2 are believable, but let's assume that we also guessed -1/2 correctly, just by eyeballing the picture correctly. Okay, now can you tell me what should I put here? What should I put under that question mark? I'm sure you guessed it correctly. That's my leading coefficient. So just a reminder, an arbitrary polynomial can be factored as a times x minus x1 times x minus x2 and so on, all the way to x minus xn, where these guys are the roots of the polynomial. How many roots? Polynomial of degree n will have n roots. They may coincide, so they may coincide. And you always need to put the leading coefficient, in this case the number 2, you always put it in the front. So we always have a factorization like that. Okay. So if our eyes did not deceive us, this here would have to be the factorization of our cubic. So if our eyes did not deceive us. So how can we make sure that our eyes did not deceive us? Well, it's very simple. I can just take that polynomial and I can uncover all the parentheses and I can check whether I get 2x cubed plus 5x squared plus x plus 2. That will remove any ambiguity, or that will remove any fears that I have not interpreted the picture correctly or that my eyes deceived me. So let's do exactly that. So let's take 2 times x minus 1 half times x minus 1 times x plus 2 times x minus 2. And what I'm going to do is I'm going to distribute all the parentheses and check that I get exactly what is written over there. So first I'm going to distribute 2 over here. So I'm going to get 2x. Minus with minus gives me plus. So 2x plus 1 times x minus 1 times x minus 2. Next, I'm going to first distribute these two together. And I'm going to keep 2x plus 1 in the front. So I'm getting x squared minus x. Let's be more, minus 2x minus x plus 2, right? So this guy with this guy, and okay, so x squared minus 2x minus x plus 2, that gives me 2x plus 1 times x squared minus 3x plus 2. Now, when you uncover parentheses, and you have done a significant chunk of work, it may be a good idea to visually check your work. So let's see, negative 2 times negative 1 is indeed plus 2. Negative x minus 2x, that is indeed negative 3x. So that looks correct. So let's continue. Now I'm going to multiply 2x with every one of these terms, and then I'm going to multiply 1 by each one of them. So I'm getting 2x cubed minus 6x squared plus 4x, so this guy with each of those three, plus x squared minus 3x plus 2. Okay, so now I'm getting 2x cubed. This term and this term can be combined, so we can combine like terms. Minus 6x squared plus x squared is minus 5x squared. Oh, that looks like good news, no? And 4x minus 3x, that is plus x. Is that good news? Yes, it is. And finally, we're having the number 2, which is good news as well. Okay, so our factorization is correct. Once again, what did I do? I plotted the cubic, I eyeballed the factorization, but then to remove the guesswork, to be sure that my work is correct, I just uncovered the parentheses, and that ensured that my factorization is correct. Okay, now the left hand side, so this side here, vanishes when x is equal to negative 1 half. It vanishes when x is equal to 1. And it vanishes when x is equal to 2. So when x is equal to 2, this cubic vanishes. So these 3 points, negative 1 half, 1 and 2, split the real line into 4 intervals. The interval from negative infinity to negative 1/2, this interval here. Next, the interval from negative 1/2 to 1. Next, the interval from 1 to 2. And finally, the interval from 2 to infinity, this interval here. Okay, so here are my 4 intervals. The interval from negative infinity to negative 1/2, from negative 1/2 to 1, from 1 to 2, and from 2 to infinity. Okay, so now let's see what are the signs. Now, this is quite a laborious work, so I'm going to ask you right now to pause the video, copy this table, and try to fill in the signs of all the expressions. So try to fill in the signs of all the expressions, and then tell me what are the signs that I should put in here. So these signs would record the sign of the function f. So this is the function f here, as x varies in the corresponding intervals. So please pause the video and carefully write down the answer. Fill in this table. I'm sure you guessed it correctly. The signs go like this: positive, negative, positive, negative. Here's how we know this. When x is between 2 and infinity, so over this interval. So when x is between 2 and infinity, this term here is positive, this term here is positive, and this term here is positive, right? Because if you pick an arbitrary number x between 2 and infinity, say x equal to 10 billion, you're getting something positive here, you're getting something positive there, and something positive in this term. So you're having the product of 3 positive quantities. The product of 3 positive quantities is necessarily positive. Okay, what happens over this interval? Well, see, what is going to happen is the following. Imagine that the variable x is moving along the real line. So when the variable x is moving along the real line, what happens with the value of the function? Well, as x crosses, so as the value of x moves across the point x equal to 2. So as the value of x moves across this point, what happens? This term, x minus 2, this multiplicative term here, changes from having been positive to negative, right? Because x just became, as x moves across 2, x just became smaller than 2. It used to be greater than 2. So x minus 2 became negative. So this term, the last term, moved from positive to negative. And the other terms, they cannot change sign because we have not passed through their zeros, right? X hasn't gone across their zeros. So I'm guaranteed that the next 3 factors have signs plus, plus, and minus. I'm guaranteed that, and notice that I did not actually need to choose any sampling points or do any substitutions. I just used common sense. Same story with the next intervals. Now suppose that x moves between those 2 intervals. So suppose that x transitions from the interval between 1 and 2 to the interval between negative 1/2 and 1. Well, this term is going to keep its sign, but this term here, the term x minus 1, since we just went across its 0, this term is going to change from positive to negative. So this term here is going to change sign. This term here is going to change from positive to negative, and the other terms will remain unchanged. So exactly one term is going to change sign. And finally, as we transition from this interval into the final 4th interval, we are getting that these 2 terms do not change signs, but the last term, x minus 1/2, So this last term is going to change from positive to negative. Altogether, we're going to be having 3 negative signs. Okay, now when we have 3 positive signs, when we multiply them out, we're getting something positive. Then we're getting something negative, 2 pluses and 1 minus giving me a minus. Then we're having 2 pluses and 1 plus and 2 minuses. Minus times minus is of course plus. And finally we're having 3 minuses. Minus times minus is plus, and then plus times minus is minus. So my signs are plus, minus, plus, minus. I don't know if you noticed, but in this cubic, the signs alternated. So if the sign in this interval were positive, then the next sign was automatically negative, and then the next sign was automatically positive, and then the next sign was automatically negative. This is almost always the case. There are exceptions, but most of the time that's the case. So most of the time, here's what happens. If you can determine that your function is positive for one single interval, then you can automatically fill in the rest of the signs by just alternating them, plus, minus, plus, minus. This is not a 100% recipe. It may fail. When does this recipe fail? So, signs alternate from plus to minus. When does that happen? When there are no powers in the polynomial factorization. Actually, when there are no even powers. This is actually the full recipe. So if there are powers in the polynomial, so suppose that I was having a bigger polynomial than this one, and suppose that in the factorization of the polynomial I had squares, right? So say that I had some different polynomial, not this one, and when I factored it out in the end I had a square here, okay? So when that happens, and maybe a square here or a fourth power here, if I had such a factorization with a fourth power here and a second power here, then I cannot use this alternating sign rule. I cannot use plus minus, plus minus, plus minus. In fact, the full recipe says that I should skip the squares, right? Because squares and fourth powers, they do not affect the sign of an expression. So in other words, if you're having a polynomial factorization and you see only first powers here, you can directly say, well, look, you can directly just figure out one of the signs in one of these intervals and then automatically fill in the rest of them, okay, without thinking too much. If all the powers that you see here are first powers, then you're good to go. Actually, the same recipe holds when all of the powers are odd. So if you see one first and say fifth power there, then you can always do the same as well. Of course, the leading coefficient, it does not affect the positivity or negativity of the expression, so I bravely ignored that term. Okay, so we're done with this tricky part. We're now ready to, actually there's little left in this problem, we're ready to write down our final answer. Our final answer is x belongs to the interval between -1/2 and 1, union with the interval from 2 to infinity. So this interval, union with this interval here. Right, this is where our function was positive. This guy and that guy, right? Because our function was positive over these two intervals, and we're looking for something which is positive. That's it. One final detail. Why did I use open parentheses there? Because I'm having a strict inequality. So when my equality is strict, so not, so this is non-strict. But when my equality is strict, so when the equality is strict, I have to use open parentheses for my final interval. This completes the problem.